Hi friends, today we are going to see the second part of the Newton's inventions. So be prepared and listen it peacefully. In this video, we are concentrating on his most famous inventions: light, prism and color. First, prism. His experiments passing sunlight through a prism led to the discovery of the heterogeneous corpuscular nature of white light. Color. The aspect of any object that may be described in terms of hue, lightness and saturation. In physics, color is associated especially with electromagnetic radiation of a certain range of wavelengths visible to the human eye. Radiation of such wavelengths constitutes that portion of the electromagnetic spectrum known as the visible spectrum, that is, light. Beginning with Kepler in 1604, the study of optics had been a central activity of the scientific revolution. Newton fully accepted the mechanical nature of light, although he chose the atomistic alternative and held that light consists of material corpuscular in motion. The core of the Newton's contribution had to do with colors. An ancient theory extending back at least to Aristotle held that a certain class of color phenomena such as the rainbow arises from the modification of the light which appears white in its pristine form. Descartes had generalized this theory for all colors and translated it into mechanical energy. Through a series of experiments performed in 1665 and 1666, in which the spectrum of the narrow beam was projected onto the wall of the darkened chamber, Newton denied the concept of modification and replaced it with that of analysis. Basically, he denied that light is simple and homogeneous, stating instead that it is complex and heterogeneous, and that the phenomena of colors arise from the analysis of the heterogeneous mixture into its simple components. The ultimate source of Newton's conviction that light is corpuscular was his recognition that individual rays of light have immutable properties. In his view, such properties implies immutable particles of matter. He held that individual rays excite sensation of individual colors which they strike the retina of the eye. He also concluded that rays refract at distinct angles. Hence, the prismatic spectrum, a beam of the heterogeneous rays that is alike incident on one face of the prism, separated or analyzed by the refraction into its component parts, and the phenomena such as the rainbow are produced by refractive analysis. Newton returned to reflecting telescopes. He constructed the first ever built. The heterogeneity of the light has been the foundation of physical optics since his time. Rather, the theory of colors, like his later work, was transmitted to the world through the Royal Society of London, which had been organized in 1660. When Newton was appointed Lucasian professor, he His name was probably unknown in the Royal Society in 1671. However, they heard of his reflecting telescope and asked to see it. Pleased by their enthusiastic reception of the telescope and his election of the society, Newton volunteered a paper on light and colors early in 1672. Vision is obviously involved in the perception of color. A person can see in dim light, however, without being able to distinguish colors. Only when more light is present do colors appear. Light of some critical intensity, therefore, is also necessary for color perception. Finally, the manner in which the brain responds to visual stimuli must also be considered. Even under identical conditions, the same object may appear red to one observer and orange to another. Clearly, the perception of color depends on vision, light, and individual interpretation, and an understanding of color involves physics and psychology. An object appears colored because of the way it interacts with light. The analysis of this interaction and the factors that determine it are the concerns of the physics of color. The psychology of color involves the eyes and brain's responses to light and the sensor data that produce. The psychology of color is invoked when the mind processes visual data, compares it with the information stored in a memory, and interprets it as color. Aristotle viewed color to be the product of the mixture of the white and black, and this was the prevailing belief until 1666, when Isaac Newton's prism experiments provided the scientific basis for the understanding of color. Newton showed that prism could break up white light into a range of colors, which he called the spectrum, and that the recombination of these spectral colors recreated the white light. Although he recognized that the spectrum was continuous, Newton used the 7 color names red, orange, yellow, green, blue, indigo, and violet for segments of the spectrum by analogy with the 7 notes of the musical scale. The unexpected difference between light perception and sound perception clarifies this curious aspect of color. When beams of light of different colors, such as red and yellow, are projected together onto the white surface in equal amounts, the resulting perception of the eye signals a single color to the brain, a signal that may be identical to that produced by a single beam of light. Newton demonstrated that color is a quality of light. To understand color, therefore, it is necessary to know something about light. As a form of electromagnetic radiation, light has properties in common with both waves and particles. It can be thought of as a stream of minute energy packets radiated at varying frequencies in a wave motion. Any given beam of light has specific values of frequency, wavelength, and energy associated with it. Frequency, which is the number of waves passing a fixed point in space in a unit of time, is commonly expressed in units of hertz. 1 hertz is equal to 1 cycle per second. Wavelength is the distance between corresponding points of two consecutive waves and is often expressed in units of meters. For instance, nanometers. 1 nanometer is equal to 10 raised to minus 9 meter. Light is not the only type of electromagnetic radiation. It is in fact only a small segment of the total electromagnetic spectrum, but it is the one form the eye can perceive. Wavelengths of light range from about 400 nanometer at the violet end of the spectrum to 700 nanometer at the red end. As shorter wavelengths, the electromagnetic spectrum extends to the ultraviolet radiation region and continues through X-rays, gamma rays and cosmic rays. Color circle. Additive mixing occurs when beams of light are combined. The color circle, first devised by Newton, is still widely used for purposes of color design and is also useful when the qualitative behavior of mixing beams of light is considered. Newton's color circle combines the spectral colors red, orange, yellow, green, cyan, indigo and blue-violet with the non-spectral colors magenta, a mixture of blue-violet and the red light beams as shown in the figure. Colors that are diametrically opposed on the color circle, such as yellow and blue-violet, green and magenta, or cyan and red. Intermediate colors can be produced by mixing light beams. So mixing red and yellow gives orange. Red and blue-violet gives magenta, and so on. The three additive primary colors are red, green and blue. This means that by additively mixing the colors red, green and blue in varying amounts, almost all other colors can be produced. Let us continue the remaining biography in part 3 video. Please like it, subscribe it and share it with friends. Thanks for watching.